Hello, everyone. Welcome to my poster and a small presentation on frontal polymerization of a thin film on wood substrate. In this research, we will be learning about a new way to coat materials via frontal polymerization. What is frontal polymerization? Frontal polymerization is a technique in which monomers are converted to polymers via localized heating. Due to the exothermic nature of reaction of monomers, heat is generated and that heat further polymerizes more monomers. For example, this is a test tube containing the monomers. An external heat source is applied, which initiates the polymerization with the help of a thermal initiator, which decomposes on heating. Then the heat source is removed and the front propagates on its own without any further use of external source. For this research, the monomers we used are a TMPTA, trimethylol propane triacrylate. It is a functional acrylate, and the initiator as Luprox 231. It is a very good thermal initiator. The important aspect in frontal polymerization of coating was to select a working viscosity so that the films are drawn and they don't flow out, or the resin is not too thick that we are not able to draw the films. And also we need a critical film thickness so that the front propagates neatly and cleanly. It doesn't stop in between. For that, the monomers we used are TMPTA, as I mentioned, and initiator as Luprox 231. To control the viscosity, we used aerosol 202, it's fumed silica. And then, like for further investigation or detailed uh, discussions about how the front velocity and front temperature is impacted, we used calcium carbonate and graphene nanoplatelets as fillers. So as we can see in the graph that viscosity plays an important role, and with hit and trial, we found that 3 PHR fumed silica was required in the formulation mix to achieve a workable viscosity. When we started making coatings and doing the frontal polymerization heated with a heat gun, we found out that 15 mils is the minimum gap in the drawdown bar required for the front to propagate neatly and cleanly. If this gap in the drawdown bar with which we are making films is less than 50 mils, then the front doesn't propagate. The material is not enough, or there is not enough heat generated, which can further polymerizes the monomers. Next, we tried to investigate how uh, by incorporation of fillers, how the front viscosity and front temperature is changing, front velocity and front temperature is changing for that. And also it gives us idea that how much amount of filler can be loaded in the base formulation, that is the maximum limit. So we started with calcium carbonate and we incorporated 5 PHR, 10 and 15 and 20. But we found out when we added 20 PHR calcium carbonate, the front stopped. It doesn't propagate on itself, probably because the monomers are less and the heat isn't enough for the further polymerization. And we also see that increasing the amount of calcium carbonate, we did see an increase in the front temperature because calcium carbonate provided a masking effect and doesn't let the heat escape. The front velocity was not much impacted. With graphene nanoplatelets, we were only able to load 5 PHR because these are nano in size and occupies a lot of space. The front velocity decreased with the increment of graphene nanoplatelets because in the research it is previously shown that graphene nanoplatelets quench the front. They uptake the free radicals and slow down the front. Also, we see a decrease in the front temperature, which is in complementary to the previous findings. Then we moved on to investigate that we are polymerizing double bonds. What is the extent of reaction? For that, we used FTIR, and on the left-hand side, we can see the resin curve as the red one and the cured film as the blue one. With the help of a ratio of C double bond O to the C double bond C, we were able to find out that 80% of the double bonds have been uh, reacted while making the films through frontal polymerization. Next, we studied the properties of the coatings, and on the left-hand side is shown as the pendulum hardness, how hard the coatings were. For some of the coatings, I was not able to get the hardness because the surface was uneven, but most of the coatings were in range of 30 to 40 seconds and moderate hardness. Then we had another resource with which we studied the surface profile of the coatings. And here are the CT scan images of the coatings. Top row shows the base, surface, interior, and near substrate, means like the part which is near to the substrate. Interior is somewhat 50% depth, and surface is on top. As we can see that there are pores in the middle of the coating, and the coatings are uniform, and the pores of the graphene coatings are very different from the pores of the calcium carbonate ones because they are two different types of fillers. We were also able to get the porosity values for each coatings we studied, and we found out that base coatings has 30% porosity, while when we incorporated calcium carbonate, the porosity increased to 42.56%, whereas with graphene nanoplatelets, the porosity increased to 36.05%. In all, we can say that incorporation of fillers increased the porosity, whereas when we compared as compared to the base formulations. In the end, I would like to thank in conclusion, I would like to say that we were able to formulate thin films using frontal polymerization on wood substrate. Their front velocity and front temperature can be controlled, and their porosity can also be controlled. And we did get a 80% conversion of monomers. These coatings are 100% solids, and they are on-demand curable coatings. In the end, I would like to thank my committee members, Dr. Mohi, Dr. Webster, Dr. Koyman, and Dr. Rajni Pillai for their support and guidance in this project. I would like to thank Chunju, Eric, and other members, especially my funding agency and my department who gave me opportunity to conduct this research. Thank you.